If everything goes according to plan, the next new nuclear power plant in the United States will not operate with water, as most of them do. Instead, it will operate with liquid, molten sodium metal. This is TerraPower and their Natrium power plant project. Here's how it works. TerraPower is a self-proclaimed nuclear innovation company. Founded by Bill Gates in 2006 and partially funded by the Department of Energy, TerraPower is one of the few private nuclear development and design companies that is making real progress on both of those fronts. I was invited to tour TerraPower in the February of 2025. In part 1 of this sponsored series, you saw the science behind turning nuclear waste into cancer medication. Here in part 2, we will talk to the scientists, engineers, and other professionals who are bringing online a Natrium nuclear reactor, and it's poised to be America's first next-generation reactor. But first, what does next generation mean for nuclear reactors? Like any commercialized technology, nuclear reactor designs have varied a lot over the last 7 decades. Most are pressurized, some are not. Most are slow, some are fast. We will define those terms later, but what you need to know now is that no matter the reactor design, you can categorize them by how they perform generally. Safety, efficiency, cost, and that's how you put them into different generations. The first generation of nuclear reactors were prototypes, inefficient. By generation 2, we had figured them out enough to deploy safe, reliable designs all over the world and operate them for decades. Generation 3 reactors got even better, even safer, standardized, and modularized. Currently, we're in the Generation 3+ era. Nuclear has gotten even more economical, but it still relies on basic physics and designs from the 40s and 50s. Generation 4, if we ever get there in a significant commercialized way, is the true power of the atom. The reactors outcompete just about everything. They use even safer fuel and produce even less nuclear waste. This is where TerraPower comes in. What TerraPower wants to build is a so-called sodium-cooled fast reactor. It's a nuclear reactor that still uses spicy uranium rocks to make steam, but the processes and materials are different. What makes it fast is the fact that it doesn't use slow neutrons that are slowed down by a moderator. Instead, it uses enriched fuel without a moderator to sustain the chain reactions. Most importantly, the reactor will use liquid sodium metal as the coolant, which will in turn heat up molten salt, which will heat up water. But how can hot liquid metal be a good coolant? Conductivity.
It's sodium to salt to water. So the sodium is the working fluid of the primary system. So that's the fluid that's coming into contact with the nuclear core. And it's great because it's an excellent heat transfer medium because of being liquid metal. And then it delivers that heat to a salt system, which is a much better fluid for storing energy.
So unlike a company like Copenhagen Atomics that wants to combine fuel and salt together in a so-called molten salt reactor, TerraPower is separating them so that it can take advantage of sodium and salt's many useful properties. For one, sodium flows surprisingly well. For two, it conducts heat super efficiently. Just look at how this sample of metal can go all the way from molten back to solid in under 2 minutes. That's because the heat is flowing out of it just that fast. And because sodium is a metal, you can pump it around a reactor with magnetism. There is nothing physical in the beaker right now that is spinning that sodium. That's just magnetism, baby. Then there's the salt. TerraPower wants to employ a formula that's been used for years in the solar power industry, so its properties are already well known. In fact, some of the salt that you see here is a flavor enhancer in Slim Jims. TerraPower tells me that at working temperature, the salt transfers heat and flows just like water, which mitigates pumping problems. Maybe most consequentially for Natrium, however, is the fact that salt holds onto heat like water does, and it's denser, so that you can hold even more heat than the same amount of water could. The numbers all work out, such that TerraPower's reactor is also a thermal battery.
So you're actually using the salt tanks and you're operating your reactor at 100%. What you're doing is raising the level of salt so that there's more mass that you have to heat, and so you're keeping that heat in your salt tank and not putting it on the grid. So
Yeah,
your
yeah.
salt tanks are what is modulating, and you can load follow with your salt tanks, and your nuclear reactor just stays at 100%
Like a heat
power.
battery, like you said.
Exactly.
The heat battery part of Natrium's design is one of the keys to making it work at scale. By adding or subtracting salt laden with heat energy to the plant's energy island, their reactor can both run at 100% all the time to provide baseload power and follow what the grid is actually demanding at that time, just like solar and wind can do.
LWRs right now, not great at load following because a nuclear reactor is a diesel engine. It just wants to run at 100% power. That's the way you efficiently use fuel, is 100% power 100% of the time. The grid doesn't always need that. The grid, as far as the need for electricity, ups and downs depending on what sort of industry is coming online, people turning on lights, refrigerators, all of those type of things. And so load following, as much as nuclear power is a great base load, it can be 100% all the time. It doesn't like to come up and down to load follow. With Natrium, now we have that capability.
All of this is a smack your own forehead kind of design that seems to tick all the right boxes, if TerraPower can make this Natrium work. By the way, what is Natrium?
Where does the word natrium come from then?
So natrium is the Latin word for sodium.
Oh.
Because think of the
Asked and
periodic
answered.
think of the periodic table.
Yep.
Sodium as an element, its sign is Na, and everybody's like, "What? It's sodium? What the heck? Why?" And it's natrium. That's where that comes from. Oh my gosh, mind blown.
So, just to recap, TerraPower's Natrium reactor is a Generation 4 reactor that uses its namesake, liquid sodium, as a coolant to more efficiently transfer nuclear heat to liquid salt, an already proven technology which allows the fully powered up reactor to adjust the amount of hot salt it creates to provide baseload and chaseload power by boiling water and turning turbines to make electricity. I'm fine. The physics behind all of this have been around since we first split the atom, yet this apparently amazing technology never got off the ground. So, why is TerraPower special? Well, because they've gotten further than anyone else. A lot further.
Within 5 or 6 years, TerraPower's Natrium reactor will be making electricity in Wyoming. So that's the country's next reactor. There's a lot of news about nuclear now, a lot of good, exciting news about nuclear energy. We haven't had many new reactors in the last few decades.
So this will be the first new reactor in the United States in a long time.
Yeah, this is America's next reactor. It's the only reactor that's under review for a construction permit with the Nuclear Regulatory Commission.
We're planning on having the Kenmare Power Station online, so we're building things and doing the tests with our lab, with national labs, and other partnerships to really prove out our technology.
We can say we're pretty close to commercialization now. We are getting a commercial license from the Nuclear Regulatory Commission. It's not a prototype, it's not a test reactor. It's a 40-year commercial license to put this plant in Wyoming. So
there's a lot that's going into, hey, what has been done before? Because sodium fast reactors have existed. They existed at the FFTF in Washington. And so they've existed, they've run before, but not at a commercial scale. But that's really great technology that we can feed from. We can get that information for all of our computer models and things like that with our reactor core, so that in the end, we're using data from the 60s that when they operated sodium fast reactors, putting a 2024 spin on it as far as, hey, we want to do this bigger, more effective, more efficient, and then go from there with the NRC to say, hey, we're using this modeling from FFTF, we're putting that into our models now, and then we're adding this salt component so that, hey, we can load follow with a nuclear reactor.
So they never quite saw their day. They were put on the side, but a lot of great work was done in the US, and it got close to being ready to commercialize, but it just stopped. And so it's this like latent technology there waiting to be harnessed.
What has surely helped the process of making America's next nuclear reactor along is the fact that, you guessed it, Natrium has even more theoretical design advantages. Sodium-cooled fast reactors are safer, and that safety lowers cost.
having spent the last 10 years on this technology myself, it's one of the things I've come to appreciate the most is that it's an atmospheric pressure system. And being at atmospheric pressure takes away a large amount of stored energy that you put into a nuclear system in a light water reactor is in the form of pressure in order to keep the fluid a liquid, but also be at high temperature. You know, sodium boils at about 890 degrees Celsius, and we operate the reactor down around 500 degrees Celsius. So there's no need to pressurize it to keep it a liquid. It's hundreds of degrees below boiling, and therefore you don't have to protect against leaks as much. You can design the structures much more economically. The safety performance actually allows you to reduce the footprint that you need for the nuclear side of the plant. So if we can take everything we need for safety and pretty much put it inside the reactor vessel and store that below grade, then we've essentially reduced the nuclear footprint to just that.
All of this comes together when you realize what TerraPower and others actually mean when they say nuclear side and energy side of a plant. In a typical nuclear power plant, everything is basically on the same pad of concrete. The fuel, the reactor, the waste, the turbines. However, what the thermal batteries of molten salt allow you to do is decouple these systems into what TerraPower calls the nuclear island and the energy island. If power was interrupted in a typical plant, it would directly affect power going to the grid. But since energy in this Natrium design is stored in the salt, it's not going directly to the water or the grid. There's a buffer. This buffer is so good, in fact, that the Natrium reactor could totally shut down, fully scram like in an emergency, and the energy island would still run at 100% power to the grid. I got to simulate this on a fancy engineering simulator.
So this is our most advanced modeling work. We integrate all the design inputs so we can run the overall plant operation on this tool. As you know, this is the first of kind design. We need something we call digital sandbox. So engineers, designers, they can play around things, put things together and break things and to see how it goes.
Right here is the power output at the nuclear island. See it dropping dramatically after I hit the scram button. This is the energy output at the same time at the energy island. Solid as a rock. Of salt. Of liquid. You get it. Anyway, if you've understood everything so far, I know some of you chemistry nerds might have a lingering question, and I've seen the same question brought up by misinformation peddlers about this technology. But Kyle, isn't sodium explosively reactive with water? You know, the stuff that's in nuclear reactors and that is everywhere and also inside of our bodies? That's a great question. Fun voice. Sodium is crazy reactive, that's true. But that's why the Natrium reactor and all the experiments at TerraPower are covered with inert argon gas. And sodium isn't as explosive as you may think. You can prove that with your own two hands.
Welcome back, kids, to TerraPower and you. Today, of course, I'm joined by my colleague here who's going to show you everything you need to know about whatever's in his hand. Hey, thanks so much for being here.
Happy to be here. Here is a...
What do we got here?
This is a brick of sodium there, Kyle. It is a classic brick of sodium in that it's been exposed to air and it has a nice layer of oxide on the outside.
I noticed it doesn't really look like metal right now.
Yes, well, if we give it a good cut, we'll definitely see some of that metal.
You're telling me there's metal in there?
I'm telling you there's metal in there. I'm telling you right now, if you wanted to bend this brick of metal, you could with your bare hands.
See, now, because this kind of just looks like a nice brie to me.
Yeah, but it cuts more like Parmesan.
So, what if I can't bend it with my bare hands? Am I a weakling?
No.
Okay. All jokes aside, so this is a highly reactive, sometimes explosive metal that, because it reacts with the oxygen in the air, has formed basically what is like rust does on iron.
Yes,
so
exactly.
it's reacting with the oxygen in the air, and then it has formed this patina over it, which is keeping additional oxygen from getting from it, which is why it's not continuously doing this.
Yes.
But it's ductile enough that I can bend it and expose it.
Yes. Can actually get that cracked. But what's interesting is you can see in all those fractures, you're exposing that sodium surface.
It hasn't seen the air yet, so it
But
doesn't
very quickly, this will start to react, and it'll basically go pink and then white. And we'll really see that when we actually cut a section out of it. So on that note, it is reactive, but it is only reactive with the amount of water you give it. And a raw piece of sodium like this will never just spontaneously combust in
because
air.
there's got to be some stoichiometry there.
Yeah.
That's like, well, it needs at least X amount,
Right.
or else it's not going to do the thing.
Well, and you need it to be molten for it to actually start burning in air. And you can't, just from air, you can't get enough humidity in the air to heat up the sodium enough to actually melt it and get it to react.
Well, then why does throwing it in a lake make it explode?
Because it hits the water, heats up enough that it actually will turn some of it molten, that outer layer, and then that will react.
Oh, is that why when you do those experiments that it kind of seems like it's more firecrackery?
Yes,
like
and then,
bah, bah, bah,
and then
bah,
it'll
bah,
like
bah.
pop and jump all around.
Because
and
it's
kinda
not
skip.
reacting all at once. Otherwise, that
Yes.
would be a large explosion.
Yes,
It's
and
reacting parts of itself.
Yes, and in terms
Oh.
of explosion, what you're getting there when it's reacting with water is sodium loves oxygen. You got H2O. So sodium is grabbing that O and saying, please give me that. I want as much of that oxygen. And then hydrogen's left over saying, what should I do except be an explosive gas? And you have heat,
You have the heat.
hydrogen. Now I want you to cut a nice little thin piece here. So it looks like brie, cuts like Parmesan.
More parmy.
But you can look and see that you've exposed that metallic layer, and you can see that it really doesn't penetrate very deep within the sodium either. So that's oxidation is really a surface level phenomenon. But very quickly you'll see this start to turn pink and then eventually white. The other thing I'd want you to do is take the piece you just cut off, and you'll see the same thing, very shiny, and start to move that around a little bit. And specifically, what you'll notice is that grabbing of the height of moisture and oxygen in the air will actually start to heat this piece up a little bit, and especially as you expose more on the backside, every time you're cracking that open, you're exposing new layers.
Oh yeah, no, I feel the temperature change.
But what's nice is since it's so thermally conductive, you can just push it into the table and you'll feel it start to cool down. And it'll become, at a thermal equilibrium with our cold table, and then be back to cold. And then if you can kind of keep working it, it'll heat back up again. Of course, if it gets too hot to touch,
don't touch it.
Set it down. Sodium melts at 100. It won't get to the point where it's melting, but that's still 100 degrees Celsius. I've gotten it up to trying to work it as much as I can, up to like 70 or 80 C.
Oh, geez.
Which is still way too hot to touch. So we want to keep things in that 40 to 30 range. Or 20. Right, and then these are pieces that we cut in other tours and demonstrations. You can see they end up just having that same sort of brine on them.
I've only seen this manipulated via being covered in oil. I didn't know it was okay to handle it and massage
well, we
it.
still want to wear the gloves, and
Yeah.
really that's for the hydroxides. You have oils and moisture on your finger that when you would touch this, you would actually start to slightly react, and then you basically, the sodium hydroxide's base 14, so it's like lye, Drano. It's very caustic, so it'll turn your fingers to soap and start to melt your skin. So that's why you wear these gloves. But
is that what that does?
yeah. But other than that, the kerosene or mineral oil that they store it in, that's just it passivates sodium, so that helps kind of keep it separated from the oxygen environment. So that's the only reason to do that. For us, I put it in a paint can, backfill it with a little bit of argon, and I store it that way. Of course, that allows it to oxidize a little more, but it also helps tell our story. So for me, I like it.
Well, thank you so much for joining us. That has been incredibly informative. Kids out there, if you want to get your hands on some sodium, don't. All right, thanks. We'll see you later.
Or go to Amazon.
Oh, no, don't say that.
Well, it is on there.
You know when you're 18, you can buy some dry ice and put it in a...
I'll admit that as an engineer, I'm kind of in love with this Natrium design. It utilizes Goldilocks materials to make nuclear power production cheaper and more efficient. The salt for the thermal battery is already proven in the solar industry, and it allows for the decoupling that makes everything smaller and safer. Sodium is plentiful. It works at atmospheric pressure. It has immense heat transfer capabilities, and it can be controlled magnetically. That's just cool. Unlike thorium-based designs, TerraPower already has or is working on the supply chains for the fuel the reactor will use. The private investment and the risk-taking is there, as are the super smart scientists and engineers who appreciate truly high-quality, award-winning educational content.
Unlike many advanced nuclear technologies that we've talked about on this channel, TerraPower seems way ahead of them all. They're ticking all the boxes. They've already broken ground. They're already working with radioactive materials. They're already working with regulators and getting licenses. If I had to pick anyone to lead the charge for new reactor technology, especially in the United States, I'd have to go with them. Until next time.